Unit 6, Architectural Design. And the learning outcomes in the study guide were kind of repeated, so I had to just sort of come up with my own ones. So let me just, okay, yeah, the session is recording. So these are the learning outcomes for this particular study unit. So at the end of this study unit 6, you should be familiar with the following. You should have a thorough understanding of how architectural decisions are made, evaluate the non-functional requirements that influence the architectural design, be able to choose an appropriate architectural pattern, and you have to have the ability to evaluate the functions of each of the architectural patterns. So when you talk about architecture, what is architecture? It's not really specific to, it's a very generic term, and you find architecture in multiple fields, not just in software. So it's not just specific to software engineering. I mean, in construction, if you're building a house, if you're building someone a house, then the first point you're going to start at is drawing up the architecture of the house. And in terms of building or in construction, the architecture ultimately determines the design of the house. Okay, it determines what kind of windows you're going to be using, what kind of doors, how many bedrooms you're going to have. It defines how the house would be structured and look. And you can take that architecture, okay, the blueprint of that house, give it to someone else who's in construction, and they should be able to reproduce the same concept. So in a sense, architecture in terms of construction and software, they share similarities. But when we're talking about architecture in terms of software, we're not really looking at the design aspect of things. We are more concerned about how these different components will be able to send each other messages. Because remember, when we're building software, we break it up into components. So the big concern in terms of architecture and software is how are these components communicating with each other? Okay, so architecture is the art and technique of designing and building, as distinguished from the skills associated with construction. Okay, so when you're defining an architecture, it is speaking to the software, how it operates. It has nothing to do with how it actually is going to be constructed or built, right? So when you talk about architectural design in terms of software, architecture of a system generally shows the overview of the system. And when we say overview, we mean the system along with all its related components. Okay, so the overview of a system is also showing the environment in which the system is operating in. So it shows how the system is organized and structured. Architectural design is part of the software design process, which shows all the main components of a system and the relationship amongst the components, done in early stages of agile and incremental development. And we know from what we learned in agile development that because of the nature of agile, you don't have to predefine the requirements, so you can get a prototype to the market as soon as possible. Unlike the traditional approach, you actually have to wait until the entire project is finished. Then that's when you can release a version of the system. So in Agile, we work with the prototype, we release the early working version, and within that early working version, you're going to do the requirements engineering of the prototype. You're going to do the architecture of the system in the prototype, and you're going to do the design as well. So those are probably the three main components in any prototype. And thanks to the Agile philosophy, if we're using the Agile philosophy, we're able to give that to the customer, and we're able to measure whether these three components actually meet the needs of the company or the business. So systems in the same application domain have similar architectures, and that is true. So because these architectures work differently and they all address a specific need, applications in the same application domain would have similar architectures. Okay, if you are building a system for a problem domain in the banking industry, let's say you're building an ATM system, the requirements of an ATM system for Nedbank will be similar to the requirements of that of Standard Bank, for example. So because they're in the same application domain and the objects that exist in that particular domain, I mean, there's customers, there's bank accounts, and all of that, those objects, there's tellers, there's clerks, and so forth. So by creating an architecture, it can still be reused in other companies that you share in the same application domain as. Okay, so keep that in mind as well. So this architectural design is a bridge between requirements analysis or requirements engineering and the actual system design phase of the SDLC. Okay, and the other point I wanted to make is in study unit 5, we talked about the different layers of abstraction. And it's very important that you guys make sense of this. If we're saying the first layer of abstraction is at its highest, and this is where you're gathering the requirements. So we're talking about the first phase of the SDLC, requirements engineering. That's one of the highest layers of abstraction, because when you're defining or you finding out the facts from the customer through interviews and so forth, you're not discussing the specifics of the system. Okay, you're not saying that this must be implemented on Android and so forth. No, you're trying to find out the functional and non-functional requirements. Then if we move on a layer higher, so we're talking about now systems analysis. Now you've done requirements engineering. Now you're doing analysis. You're drawing your use case diagram and your ERDs. That's a layer higher. So here you're still being independent. You're still being platform independent in the sense that the use case diagrams and the system sequence diagrams, all your UML does not speak to a specific platform. It's just generic. You can take what you've done in analysis and give it to someone else and they reproduce the same thing on a different platform. But once you move to design, that's where it gets tricky, because with actual design phase of the SDL, so you don't have a choice but to be platform specific, because the way you design a button on Android and iOS, for example, will be different. So there you become platform specific. And what determines the platform you go with is your architecture, because your architecture shows the environment of that the system is operating in. If we're saying we want to go with Windows, then it means that the programming language you end up choosing, the code that's got these components are going to communicate in is going to be .NET based. So it's very important that you understand that architectural design is like a bridge between the time you do your requirements engineering to the time you get to being platform specific in terms of your user interface design for the platform that you are going on. So what are the advantages of doing architectural design? There is communication among stakeholders. So stakeholders communicate more, work together more in the early days of the project, because you remember that you're trying to get at least demonstrate even the architecture of the system in the prototype. So software engineers can analyze a system to see whether it meets the functional and non-functional requirements. And I said that in the earlier slide that this ties into the early working version of the system. You're able to critique it. The architectural design may be reused for similar systems, same requirements in a large scale. So that's the beauty of architecture. Architecture, unlike system design, can be reused. You can't reuse. It's very rare that you may want to reuse the UI or the user interface of another company. But architecture will remain the same. If you are a bank and you want to start an ATM system, and you reuse the architecture of a system that's created by another bank, you're not gonna keep the user interface design the same. you're going to keep the architecture the same, the architecture of the system, but the UI will change. So these are the advantages that architectural design can be reused in different case studies. So then what are architectural patterns? Another term which you can use is architectural styles. So architectural styles or architectural patterns are a way of presenting, sharing, and reusing knowledge about software systems. It's an abstract description of a good practice. Because it has been adopted multiple times and it's been proven to work, we reuse architectures that have been defined already. It's very rare that you're going to find an organization that's creating its own architecture. So we're going to adopt something that's abstract, that's a good practice, it's been tried and tested. There are several types of architectural patterns or styles which can be used to design or show an overview of a system, and we're going to talk about that in the later slides. So what influences the decision you make in terms of architectural styles, architectural patterns? How do you decide that I'm going with this particular architectural style? Okay, so it may be based on a certain architectural pattern or style. Hence, a system architect should have knowledge of the strengths and weaknesses of the different architectural patterns. So you need to know the weaknesses, those strengths and weaknesses of the different architectural patterns to make a good decision. But fundamentally, your decision will be based on the next point: performance, security, safety, availability, and maintainability. It's very rare that you're going to find that your architectural decision is based on functional requirements, because functional requirements can still be implemented regardless of platform. If you say you want a system with the login feature, it doesn't. If I'm using Windows, I can still implement that feature. If I'm using Linux, I can still implement that feature. But your architectural decision is mostly influenced by the non-functional requirements of the system. If, for example, we're using security and safety as a metric, if your customer says the level of security for this particular system that I want you to develop must be so high, then you need to make a decision and choose the correct platform that offers that kind of security. We know Windows has its weaknesses in terms of being vulnerable to viruses and all of these internet threats. So then the architecture that you choose for the system, if there's a high level of security requirements, will be maybe, for example, Unix based. Okay, so the point I'm trying to make here is that functional requirements don't play such a huge role in deciding the architecture that you choose. It's more based on the non-functional requirements of the system. Hence, that is looking into the non-functional requirements, ties into the second point. So we're going to talk about the first architectural style that you can go with. And this one is called the layered architectural pattern. I mean, there's a reason why they call it the layered architectural pattern, because it's in layers. And there's the other term for it, we can refer to it as the N-tier architecture, where the N represents the number of layers. The old style layered architecture used to only be 2 layers, and we refer to it as the client server. You may be familiar with it. We refer to it as the client server architecture. It only had 2 layers. The client layer, which is just the terminal to connect to the server, and the server layer. Okay, that's a very old school way of doing it, and they moved to a different one now. It's called a 3-tier architecture. So you normally have 3 tiers there. You have the UI, you have the business logic layer, and then you also have the database layer. So when we use the term N-tier, we're referring to all the layered architectural styles that have more than 3 layers. Most companies in this day and age choose to add additional layers for security purposes, for example, like the one you have in front of you now. You can see this one will not be called 3-tier because it has 4 layers. Even if there's 5 layers, you still refer to it as N-tier. So this one is referred to as N-tier or layered architecture, and there are 4 layers. So let's discuss what all of these layers mean. So the first layer is the system support layer. And this is where you make a decision on the operating system that will power this environment. Which operating system are we going to be hosting this system on? Because remember, the decision you make here influences what you do on the layer above. Okay, that's why we refer to layered architecture. Sometimes we refer to it as a service-based architecture, because the services that are produced by the system support layer determines how we code the system in the layer above. So if we go with, if we say on system support layer, we're going with Windows, then it means the database engine that we use as well has to be Windows-based. Okay, you cannot then choose to use Linux, although Windows allows you to do that. But if it doesn't work vice versa, if you're on Linux and you choose to go with Linux, you need to stick to Linux tools or open source tools. Otherwise, you cannot support. They don't allow you to support Windows, because Windows is proprietary to Windows. So you choose a platform, you use the tools associated with that platform in the first layer. In the second layer, the layer above it, based on the platform you chose to go with here, then it will determine the programming language which you use here. If you chose to go with Linux, then most likely you're going to be programming using Java. Okay, so the layer above the first layer is core business logic. Why do we call it business logic? The term comes from the fact that back in the day we didn't have systems. We were operating in a normal, in a very traditional way. And what had happened was we had business processes for as long as businesses existed. There was business processes. So when technology or computers came along, the computers were there or invented to automate these business processes. So whatever becomes a business process, we can transfer that into some sort of code or into an if statement. You can always turn it into an if statement or whatever. So that's where the term business logic layer comes from. But at the end of the day, you must know we're talking about the code that powers the system. So if you chose to go with Linux, then you're going to be coding your business logic layer in Java-based language. If you chose to go with Windows, then you may be using C# in the business logic layer. And if we go a layer higher, then we have a security layer. You can see that this architecture was made for very security or sophisticated system. For example, banking system where you need authentication and authorization. You need a separate layer for that. It's not good enough that you're combining it with the user interface. Some companies do that, but remember, this is the client layer, and validating at the client layer alone is not good enough. Okay, it's not the highest level of security. You can add another additional layer there where you also validating the user interface input using the server. For example, let's say here in the user interface layer, you asked the user of the system to put in the email address, and they decide to put in some malicious code there. There is a way of overriding inputs validation on the client side, so it's not that secure. They can override it and then send the information to the server, and that's how you get exploited. So adding an additional layer there of security is a very wise thing to do. And that brings you to N-tier architecture, because then you move away from the regular 3-tier architecture. Now you become N-tier architecture. So in a nutshell, that's how this layered architecture works. You can see there's different layers, and each layer has a particular responsibility. So layered architecture, the major advantage of layered architecture is that it is changeable and portable. Also, when the layer interfaces change or new functionalities are added to a layer, only the adjacent layer is affected. The layer architecture is mostly used when we are adding new functionalities to existing systems. Okay, so you use layered architecture if you're adding stuff to an existing system, and you're not really building the system from scratch. So if you adopted a system that was being used by another company, maybe you just want to change the way the system looks, so you're only going to change that user interface layer. And when there's a need for multi-level security, which I showed you in the previous slide, security at the client level, security at the server level. When the development of the system is divided amongst team members and each team must achieve a certain purpose, hence the term layered. So you can have experts at different layers, operating at different layers. So we can have people that are experts at the operating system here. We can have people that are experts at the particular programming language here. We can have people that are experts at server-side validation or security. And then we can have people that are experts at designing user interfaces or user interface designers. So what is the disadvantage of using this layered architecture? It is difficult to separate these layers in real life. So it's not an easy task, okay? Although conveniently having the layers there allows you to be able to separate them, but it's not an easy task to do so, especially if you want to make changes to some of the functionality and your changes are not just user interface based. There can be a problem in terms of functionality and performance. This can be due to having multiple levels of interpreting different service requests. So the services come from the operating system layer and they go upwards. So if there's a delay in any one of the layers, maybe the database is really overwhelmed with the amount of transactions that are there or the amount of data that is there, so it starts to become slow. That affects the whole transition of this service request, okay? Because there's multiple levels of interpreting the service request. So moving on to the next architecture, which is the repository architecture. So a repository is a shared location at which you keep data, okay? And the subsystems use and modify a shared data structure named the repository. The subsystems are relatively independent in that they interact only to the repository. So we have independent subsystems, like you see in this particular case, independent subsystems. However, the only thing they have in common is that they're sharing the same shared database. So we have a system that registers the students, the system in which students can give course feedback, the system in which the administrator accesses the data of the students, the system at which you do approval for the different people that are registering, and the system that you do the reporting on. So we have all of these different subsystems operating and accessing this shared database, but accessing different parts of it. And that's the nature of the repository architecture. And here they say that it describes how a set of interacting components or objects can share data, involves large amounts of data organized around a shared database or repository. It's most appropriate in highly data-driven applications, systems which handle large volumes of data. What are its advantages? Advantages that it's independence. The other system usually does not know that the other system exists. Okay? All they have in common is a shared database, otherwise they're independent systems. There is a consistency since all the data is stored in one place. There is consistency, but at the same time, you could run into some conflicts because remember, we have these systems that are sharing this particular, thankfully, repositories have mechanisms in place to handle, we call it concurrency of transactions. But it doesn't mean that there isn't a possibility that it could happen, that you have conflicting changes to data. So system A is making changes or requesting the data, while system B is also busy making changes to the same data entry. So there is consistency because it's in one place, but you could still experience issues. Any changes made to one component can be propagated to all components, which is true. Disadvantages: making arrangements or organizing communication to the repository is inefficient. A failure at a certain node in the repository affects the whole system. So if, for example, this one here, if the system here, this registration system is failing, then it actually impacts on the flow of the whole system, because although these are independent subsystems, they're all relying on the data that was entered by the other system. So there's no way for the administrator to approve students that are registering for a course if the registration component is not working. So at the end of the day, it affects the flow because all of these systems are contributing to the bigger picture, which is the repository. And the third architectural pattern that we're going to be talking about today is called the pipe and filter architecture. Now, it's important to understand that we build systems in terms of components, so we break them up into components. And here a component is represented as a filter. Each component, and we learned this in later study units, each component has two interfaces. We refer to it as a requires interface and a provides interface. In simple terms, each component will do input, process, and then output. And the output of a particular component can be used as an input in another. And that's exactly what this pipe and filter architecture is demonstrating. We have a data source and the data is inputted, the component does some sort of processing, it produces an output. That output of the first component is then used as an input in the other component, in the next component. And so the story continues. And I use this example, I say, picture yourself reading a book. There's different chapters. And as you go through the different chapters, they add on to the story. So the data goes from its original source to the data sink, referred to it as a data sink. So by the time it arrives at the data sink, it would have grown in value, okay? It would be telling the bigger picture. So we refer to it as the transformed version of the data. So it goes through all of these different transformations as it's going through the different filters or components, okay? So that's what we mean by pipe and filter architecture. The pipes is the interfaces. It could be input interface or output interface. The filter itself is the component. So the pipe and filter architecture is a runtime organization of a system where functional transformations process their inputs and then produce output. The other aspect of this is that this is a runtime driven architecture. It means all of this happens while the system is running and it's using up the resources. So the advantages of pipe and filter include easy to understand and support transformation reuse. Evolution by adding transformation is more straightforward. What are some of its disadvantages? There is increased system overhead, which can lead to incompatibility issues and can be difficult to reuse. Okay, so it can also be a challenge because since it's a runtime architecture, you need to find components that will sort of take up the same amount of system resources, because you don't want to integrate a component into this pipe and filter architecture that is going to hog up all the system resources at runtime, and then the process only shuts down here. So you need that to strike a balance between your components, make sure they're compatible in terms of the amount of resources they need for processing. Each transformation must pass its input and unpass its output in an agreed form. So your components need to be communicating or structuring the output in the same format that the next component is expecting the input in. So in a sense, your components have to be speaking the same language. They need to be understanding each other. So that's the other disadvantage. There should be stipulated there should be a stipulated format for easy readability and understandability across all the platforms. Okay, so it requires some level of standardization between these components. So when you talk about application architecture, they are developed so as to meet a business need or organization need. Application architecture can be used by software designers as a starting point for the architectural design process. So software designers, people who design the user interface, the way the software looks, the application architecture is a starting point because it determines the platform at which the designers are going to be working on. So they can see, okay, in the architecture, this is using a .NET or Windows-based architecture, which means we also have to use for example, design the system in Visual Studio. So it's definitely a starting point for the design process. As a design checklist can be used as a design checklist, as a way of organizing the work of the development team, as a means of assessing components for reuse, okay? So that's the nature of application architectures, or using architecture in applications. So let's see a couple of examples at which or what kind of systems that these architectures can be used in. The pipe and filter architecture is most applicable in systems that process transactions. These are interactive systems which allows users to make asynchronous requests for a service. Okay, so pipe and filter, we have a transaction processing system. For example, if we're talking about an ATM system processing a transaction, there's a different component that handles validating the card. There's a different component that handles the printing of the receipt after you've performed the transaction. There's different components that handles communication with the database server. So all of these components, okay, you refer to them as filters. As you insert the card and start authenticating the transaction, the data goes to all these different filters and it goes through some level of transformation. Okay, so that's an example of pipe and filter. We have these pipes, these inputs and outputs interfaces, and then you have the filters, the components that make up the system, and the data has to flow through these different components. And then your information systems, typical information systems use the layered architecture. The reason for this is because when you have an information system, you want the data to be consumed using different devices. This could be mobile devices, desktops, or tablets, or whatever, laptops. So you want the data to be consumed using different devices. Hence, you're going to use the layered architecture, because with the layered architecture, all you need to do is make changes to the user interface layer to accommodate the different systems. So if you're building it for a web-based system, then you're going to be in the user interface layer, you're going to be writing HTML code. But the business logic layer would already exist with the functionalities. So all you're doing is changing the display or the design, what the customer sees. So that's an example. Information systems are a critical example of how we would use the layered architecture. And then we also have the repository architecture. Language processing systems. They translate one language into an alternative representation of a specific language. If we use a compiler on a computer as an example, the compiler has to compile the code so it translates whatever programming language you're writing it into machine readable code. Okay, so those instructions for the different syntax of, for example, Java and C# and C++ will be stored in some sort of repository on the system software. Okay, and all of these programming languages are able to make reference to the repository for immediate translation. So compilers, system that translates language from one language to another specific language, or an example of a repository architecture. All of these different IDEs and with compilers are able to translate a language to a machine language using repository architecture. So in conclusion, design is concerned with the overview of the whole system and is a critical link between design and requirements engineering. Architectural design is done as a way of communicating with the stakeholders, systems analysis, and for large-scale reuse. The three main architectural patterns are the layered architecture, which separates layers and they are independent of each other. Then we have the repository architecture, where there's a shared or large volume of data that is shared in a single database or repository. Then we have the client-server architecture, which forms part of this layered architecture. It's just that it's going to be two-tier architecture, the client and the server. Which there's a main hub, which is a server with several clients sharing information and services. And then lastly, we have the pipe and filter architecture, inputs data undergoing a process of transformation to produce outputs. Okay, So that is a wrap of study units 6. Do you guys have any questions regarding this study unit? You're fine, you're happy. When you're quiet, I assume you're happy. You can unmute yourself if you have a question. Okay.
Hello, sir.
Yes, Eugene, how are you?
I'm alright, sir. How are you?
I'm good, thanks. What's your question? Do you
That's a
have a
question.
question?
No questions, sir.
No question, you're happy? Okay.
Yes, sir.
All right. Then, guys, we'll have to then regroup. I see. Mohammed, do you have a question?
Yes, sir. How are you doing today?
I'm good, and you?
I'm good. Thank you so much. I just wanted to query if we will be doing any assignments for this period before the exam.
Did you do the first one?
Yes, sir.
No, we're only going to be doing MCQs. So you've done the first assignment, you've done the test. By the way, how did you guys find the test? What do you think of the test?
For me, I found it was I found it enjoyable. I don't know if that's an exaggeration.
It wasn't difficult.
Yeah. So
no, that was a very easy test, guys. I mean, if you find that difficult, I'm really sorry for the exam, because remember that was just unit 1 to 5. Now when you have to do the whole study guide, that was the stuff that I included there in the test was mostly the stuff that we discussed in the slides specifically. I mean, even the case study was that of an ATM, and you are asked to draw the use case diagram for an ATM and the entities, or the ERD as well, the domain class diagram. So everything just came from the slides. Okay, so you've done the assignment, you've done the test. Now you just have to look out for the MCQs. Okay, so I think 1 to 5 is already there. Then 6 and 7 is the next one we're gonna get. Okay, and then after that is the exam. And that's all you guys have.
okay, so does this apply for every subject?
Every exit level theory subject will share that structure. In actual fact, all exit levels subjects remain in the old structure pre-lockdown. It's just that they substituted the group assignments for MCQs.
Excellent, sir.
Yeah, that's all it is.
What I liked about this test is that there was no scope creep, and which happened to another subject. But anyway,
yeah, the scope creep is always there. No, I told you guys, I'm promising you this. Even the waterfall, that revision classes that we had, I said to you guys, this may come out, okay? And the waterfall was there. The easy marks to score. I think it was like 20 marks. Yeah, I think you had to draw one and you had to discuss the advantages and disadvantages. So I wasn't going to catch you guys off guard. And same thing applies to the exam. Just follow whatever we do in the class, and then you'll be fine. So are there any other questions, guys, before we wrap up the session? Okay, then we'll just regroup Friday. Yes, I see Tando. You have your hand up. You can ask or unmute.
Oh yes, sir. Where can we find the slides for today's lesson?
Oh, that one I'll have to upload. I upload them usually after Friday's lesson, each Friday's lesson. But I'll upload it. I can upload it today for you guys if you want to look through them as well.
Okay.
With the recording as well for those who are not here. Yes, Neo.
Yeah. How are you, sir?
I'm good, and you?
Great. So could you please take the liberty to upload exams on the past paper exams on the portal?
Okay, yeah, I'll source some of them for you, although it's very difficult to find I'm only finding like from 2016 stuff like that. But I'll thank you for notifying me earlier. Then I have a chance to source them from. I'll probably have to ask from the exams office or someone from head office.
Oh, all right.
Yeah. Then I'll include it there as a section on the portal. So
All
you
right.
guys can.
Thank you, sir.
Okay. Okay. So thank you guys. We'll regroup on Friday again.